Is first of all, we'll have Vita talking about doing an introduction to the topic, and we'll also present on the new white paper that Leviat's published that encourage you all to have a look online after the session. Then we'll be joined by Liang, who will be doing a demonstration of some of the software from Leviat. Then Harriet Cotton will get into the main meat of the session, and she'll be talking about the developments that are coming in the new Eurocode. And then my colleague Carol Gillerud will be talking about RAM concepts and how you can implement some of the changes using finite element analysis software. So the session will be about 45 minutes, and if you can keep your questions to the end, we'll do a Q&A session at the end. Just a little bit of housekeeping. The fire escapes are out and round the back of the auditorium or out the front door that you came in, and there are toilets on both levels. The men's and disabled are on this side of the reception, and the women's are on the other side. And afterwards, we've got some drinks and quite a lot of food, it looks like, upstairs. So you're welcome to join us upstairs after the session for quite a few drinks and nibbles. So please stick around for that. So yeah, as I said, we'll be talking about the white paper, and then we'll be talking a little bit about the code changes and how you can implement them using our software. But I'll invite Vita to come up first.
Thank you so much, Jennifer, and thank you everyone attending tonight in such a cold evening. So I would like to give you a little bit of overview about white paper. So Leviat's white paper addresses punching shear risks. Also, we review Leviat solutions to punching shear and case studies, design tools and software. Also, some global structural design codes and standards, which Leviat also uses for our software packages, and alignment with evolving standards such as Eurocode 2 second generation, sustainability objectives, industry best practice. I wanted to start introducing our white paper just by reviewing a few case studies, which you can find a bit more in depth in that white paper. So just to remind you about the danger what punching shear can cause. So the first case study, Samsung department store in South Korea, Seoul, probably the largest collapse in the history. It happened because of overloaded structure due to the serious shortcuts during the construction process. So effective slab depth and column sizes were reduced during construction, which caused punching shear collapse. The second case study, Charles de Gaulle Airport, Terminal 2E, where vaulted precast concrete shell roof was under-reinforced, and it was actually supporting through some metallic fixings and studs. It was supporting the glass facade, and due to temperature differences, due to not enough reinforcement in the precast shell, it collapsed. So this case study shows that it can happen also in the precast elements, in the more complex structures. So it's important to consider punching shear in those cases as well. And the third, Champlain Towers in United States, which caused 98 fatalities, brought global attention, which is still investigated or under investigation. So slab column connections in the pool deck area due to the concrete deterioration, due to the steel reinforcement corrosion, also caused punching shear failure. And the last case study, Piper's Row Car Park, is very familiar to all of them, all of you probably. So the great thing was that the car park was closed already, and punching shear failure occurred on the just under the dead load alone. Here you can see some solutions to punching shear, which are available from Leviat. You probably are familiar with Halfen and Encon brands. They are now under Leviat umbrella. So Halfen is producing HDB range, which is more like a modular system available in standard lengths and standard heights. It is an ETA approved system, and the benefit of this system is that you can reduce shear rails by about 20 to 30% compared to other case approved systems. The HDBZ is not that well known in UK. It's more for European and Middle Eastern markets. It's optimized to reduce foundation depth, deliver savings in excavation, time, and also material. And ShearFix, probably the most well-known software and the most well-known product in UK, which is usually pre-manufactured to order, and probably around 80% of the engineers are using this software. DuraCage and Head are systems which are designed to carry very large shear loads at slab column support. And Rhino Bar is used for strengthening flat slabs and for the retrofit projects. So that's just a brief introduction. Also, in terms of the digital trends, at Leviat, we have BIM plugins for Revit, Tekla, and Allplan already provided in our libraries. And also together with Bentley, we do have a plugin with Bentley software for the ShearFix. Here you can see some global standard design codes and global design codes, which are available in our software packages. I just wanted to mention that Swiss code is actually part of the critical shear crack theory, which is adopted now in Eurocode 2. Slightly different version, slightly more close form and refined way, but Harriet and Paul will talk about it in more detail. So you all got the summary comparison where we're comparing first and second generations of Eurocode 2 and what will be the impact for the designers. So it will help you to understand all the changes much better. Thank you. I would like to pass it to Leanne.
Good evening, everybody. It's good to see some familiar faces down there. My name is Lian. I'm the technical team lead for the Stretch Connection department for Leviat. So, punching shear. Eurocode 2, Part 1, Clause 6.4. You know, when I was a student, let me just reflecting on my student career there. You know, one of the worst things I don't want to do is punching shear calculation. Do one. Don't get me wrong. There's a quite straightforward flowchart already set up for us to follow, but do one column might take a while. You know, scale that up to a full project, you end up with dozens of different types of columns that sort of expand your workload a lot. So we need a quicker way to do this. ShearFix is one of the software that we offer to everybody for free on our website that you can use, design it. You know, some of the structural engineers here or structural engineers joining us online, you know, may already be familiar with it. I'm going to show everybody a quick demo of how the ShearFix looks like. Now, if you focus on this row here, as you can see, you have the freedom to change the national annex values if you need. You will have the option to change the column location as well as the column shape. Let's start from here. You probably want to reference the column name and floor level and number of columns very clearly in the beginning of the project. Otherwise, it got very messy towards the end of the project. You can also dictate the dimension of the column. In this case, we selected an edge column. You can then dictate how close or how far you want it to be away from the column edge. Let's go to another tab. Of course, you'll be able to play around with the slab thickness. You know, if you have a slab difference on two sides, you can also do that and dictate the concrete grade, the cover, as well as the pre-compression value. Reinforcement is a key. You have two ways of inputting reinforcement into the design of shear fix. You can either put it in a layer input way, so T1, T2, B1, B2, or you can use the ratio input as a general rule to design for it. Loading side, we do have three options for you to calculate the eccentricity factor, beta factor. So you can either use a UKK approved calculation method to calculate beta value, or using the default value based on a applied shear load, or if it's a very bespoke case that you've done CAD calculation for, you can always select the input value and input the beta value calculated in your specific case. Openings, as you can see here, we've got a little openings just next to this column. This software will also allow you to design for that opening. You will get to dictate how big the opening is and how close or far away from the column. It will have an impact on the final design. Shear fix layout here on the last tab, you will have the option to either use software automated generated layout for this, a radial layout, or a cruciform layout. You will also be able to choose the stud diameter if you need, well, as long as it satisfies the design requirement. You can also have the option to change from a top down and a bottom up, depends on your slab situation, as well as the first stud spacing from the column. And if you have a larger elongated column, you have two input options. Now we'll talk about this in more detail in later slides. When you finish the design, you will be able to click here for preview. I'm not going to show everybody here because it will be a long report, but you will be able to visualize a very tidy and accurate calculation report. Now, this is just an overview. At this point, I kind of wished I knew this when I was a student, right? But jokes aside, if this, I know iStruck does have a large audience of student members out there. If you're watching this and laughing now, I would urge everybody now to go into the detail and learn everything from first principle. So when you get to the industry where you start to use design software like this, you will be able to assess the outcome based on your engineering judgment. Thank you. I will pass the stage to my colleague Harriet, which will talk a little bit in more detail regarding what's new of the second generation of Eurocode.
Thanks, Leanne. My name's Harriet Cotton. I'm an R&D engineer at Leviat. So I'm going to guide you through the changes to the punching shear design from first generation to second generation. The latest version of the latest publication of the first generation was in 2014, and that was along with the UK National Annex. Second generation was published in 2023, but that was just the main document. We've only just seen the UK National Annex, so we've got a draft version of that, which is now available online and available for public comment. We're expecting the publication of the UK National Annex in February next year. So, and the first generation of the Eurocode will be withdrawn in March 2028. We will have this overlap period, so they're both going to be current documents. The second generation, it's not recommended you use that until you've got the publication of the UK National Annex. So we're approaching what we anticipate to be a 2-year overlap period where we can transition between first generation and second generation, get used to the new rules. Yeah. So I'm going to talk through those changes. The key thing to take away, if the detail gets a bit blurry, is that they're substantial. Moving from an empirical design model to a theoretical design model. I think it's already been mentioned, but the type of reinforcement used now comes into the code. So first generation code assumed the use of links or stirrups. Now there's flexibility for different reinforcement systems, such as the double-headed shear studs, which we have with Ancon Shearfix and Halfon HDB. And from initial investigations, it appears as though some designs are more conservative. So by that, I mean there's more reinforcements required for a design. And to show a quick snapshot of some example calculations, for the same design input, the image on the left shows a solution using the first generation, and the image on the right is the second generation. So in this design example, you can see there's an extra stud per rail in the second generation, and also some additional studs on that first perimeter. And the same applies if it's not studs, if it's links, it would be the same case, an extra perimeter of reinforcement and more reinforcement on that first perimeter. So that's a radial layout, and similarly for a cruciform or orthogonal layout, an extra stud or an extra perimeter of reinforcement and additional reinforcement close to the column face. So these are the 10 points I'm going to try and run through, and they correspond to the handout that hopefully you picked up on the way in. So starting with the location of the control perimeter. In the first generation, the location was at 2D, a distance of 2D from the column face. That changes in the second generation to 0.5D from the column face. So you can see it's moved substantially closer to the column. That's in the first generation, it didn't have a physical meaning. It was related to the empirical design model. Having the perimeter at 0.5D has a physical meaning. So that's where we anticipate the critical region for punching failures to occur. And that's the same location in most other international design codes, is at 0.5D from the column face. A minor point, the notation changes from U to B. You'll see the D value changes from D to DV as well. It's really just a change in notation. There's no significant change. DV is the shear resisting effective depth of the slab, but it's essentially the same value as first generation. Extent of the reinforcement, or in other words, the distance from the outermost shear reinforcement to the outer control perimeter. So when you're calculating a punching shear design, when you're calculating a solution, you determine the length of the outer control perimeter required, and then you fill the area with reinforcement, essentially. And the position of that outer control perimeter is determined by how long it is and what the shape is, depending on the column shape. So the initial investigations have shown that I think we're going to have similar length for the outer control perimeter in the first generation and second generation. There seem to be similar lengths, but in the second generation, the last perimeter of reinforcement needs to be closer to the outer control perimeter. And that's why we're seeing this additional perimeter of reinforcement. So in this diagrammatic image on the right, if the outer control perimeter that's shown applies to both first generation and second generation, the solution for first generation would just be those 3 studs or 3 perimeters of reinforcement. And for the second generation, we need that additional perimeter, which is shown in red. Oh, yeah, I was going to point out the DV out is a parameter that's shown here. That's slightly different to DV. It is the shear resisting effective depth of outer shear reinforcement, and it's slightly less than the DV value, which is just a new parameter in the second generation. So the other aspect, which I think seems to have a big impact on design solutions, is the stud spacing rule. So the table on the left shows the maximum tangential spacing of reinforcement for flat slabs, and highlighted in red in the second generation, we've got this new rule that the first perimeter of reinforcement has a maximum spacing of 0.75 dV. And so depending on a column geometry, that might mean that more reinforcement is required on that first perimeter. Going to point out in the image on the right, you'll see that there's actually two limits shown on the first perimeter. 0.75 dV is applicable for flat slabs. 0.5 dV is for column bases and ground slabs. So large columns is another big change in the code. So it's fairly well understood in practice that punching shear stresses tend to focus around the corners of columns, but that wasn't actually reflected in the first generation Eurocode, or not in the main part of the Eurocode. It's now included in the second generation, so the control perimeter cannot extend beyond 1.5 dV from the corner along the straights. That is already in lots of other international codes, and it was actually in the German national annex for the first generation. Fortunately, for users of ShearFix design program, we had anticipated that this would come into effect. So Liang mentioned that in the software, you have two options for large and elongated columns, and it defaults to best practice, which incorporates this limit. It wasn't officially in the Eurocode, so you can, in the software, alter that input, that option to EC2, and then it'll permit the full perimeter, full length of the control perimeter. Beta value, we get lots of questions about the beta values at Ancon, no, Leviat. In my opinion, I think it has become much simplified. On the left, there's a whole sort of collection of different beta equations that are in the first generation. And on the right, this is what's in the next generation. And you can see that it's just essentially one equation that's applicable to all columns, which I think is a lot simpler. And there's still the option to use an approximated value, and those approximated values are the same value as in first generation. There's an introduction of some values for ends of walls and corners of walls. The only other thing I was going to point out is that a minimum value is introduced, which is 1.05, which we didn't have in the first generation. So in the equation, there's these parameters EB and BB, and they've got a very similar definition as the EY, EZ, BY, BZ from first generation. So EB is the eccentricity of the action with respect to the centroid of the control perimeter, and the BB is the mean overall width of the control perimeter. The resistance formulae change. There's some strong similarities. So if we look at the punching shear resistance without reinforcement, firstly, I think I've got a pointer. Let's see if we can use the pointer. So, no, that's all right. If you work from the left to the right on those left-hand equations, you can see that there's a strong similarity top to bottom, and it's follows the same pattern until you get to DDG in the second generation. So that's a new parameter that's coming in. That's related to the size of the aggregate used in the concrete. That's to do with the roughness across a crack. And then the other changes on the first generation, you can see the sigma CP, which is for the pre-stresses in the slab. And it sort of seems to disappear, but actually there's this parameter Kn, which I've shown below it, equation 8.101. And if you have axial stresses in the slab, then you calculate this Kn value. If they are compressive stresses, you multiply Kpb by Kn. If they're tensile forces, then you divide Kpb by Kn. So that influences the whole of that equation. And then the punching shear resistance with reinforcement, Again, you can see a very similar sort of structure to the equation. You've got a portion of resistance related to the strength of the concrete and a portion related to the punching shear reinforcement, the steel that's in there. I think it's quite interesting, and it's worth sort of noting that in the first generation, we had a 0.75 value multiplying the VRDC. That's changed to E to C. And you'll see at the bottom here that E to C relates to the applied punching shear stress. So a single design solution the punching shear resistance will vary depending on the applied load. And that E to C value also comes into the E to S. So it influences both sides of that equation. There is a maximum value, which is shown at the bottom. So the maximum punching shear resistance is E to Cis. The Cis is for system, so it depends on the punching shear reinforcement system that's used, multiplied by the punching shear resistance without reinforcement. So this is where the different types of punching shear reinforcement influences the calculation. There's two parameters, dV out and E to Cis. In both cases, using a double-headed shear stud maximizes those values and sort of makes the calculations more favorable. The very bottom of the screen, you'll see that on the right-hand side, the values are taken from the main body of the Eurocode, and on the left, they're taken out of the draft UK National Annex. This is the only part of the UK National Annex which seemed to stand out to me as varying the main part of the code. The last few points I'm going to go through quite quickly because Carl's going to pick up on these as well. But just to point out that there's this is a new factor in the calculation, which is the point of contraflexure factor, i.e. the place where a sagging moment becomes a hogging moment or a hogging moment becomes a sagging moment in the slab. So if that point is close to the column head, then it can enhance the punching shear resistance of the concrete. And within something like the ShearFix software, the software can't determine what this value is. If it's included, it would need to be calculated by the designer separately and then input. And there are some rules around approximations that are permitted. Again, this is one that's sort of tucked into the, if you're using a design tool, then this will be covered by the design tool. In the first generation, it was a single iteration. You determined the length of the outer control perimeter and then filled that area with reinforcement. Now in the second generation, you can do an iterative design. Now, I don't imagine anyone will do this manually. It would just be within design tools. But for each perimeter, you would redetermine all of the parameters and decide whether or not you need another perimeter of reinforcement. So the diagram there is sort of suggesting that at each perimeter, you think of that as a new column face and do your calculation again and again and again. Now, I think the reason for this is to try and refine and maybe reduce the amount of reinforcement you would need. But I have seen some examples which increase the reinforcement through this method. So it'll be interesting to see how that kind of translates into practice. And my last point is to do with the design shear stress calculation. So this is now it's sort of explicitly included in the code that you can use detailed analysis to determine the punching shear stresses. So you don't have to calculate a beta value to apply to the punching shear stresses. If you've got a high-end FE design tool, you could use the punching shear stresses coming straight out of that tool. Carl's going to talk a bit more about this. And so that has been a whistle-stop tour of 10 points that are changing in the code. I do think the first few points are sort of the key ones, which seem to have the biggest impact on design solutions. And if you didn't pick up the handout, I'm sure there's some more on the way out. And I'm going to hand over to Carl.
That advancing. Okay, thank you. Sorry about that. And thank you, Harriet. Thank you to all of you. It's a pleasure to be here in London and a true honor to be here at iStruct with the opportunity to talk to you about the new EC2, punch and shear, and also just a little bit about me and my work. So that's where I'm going to start. I'm going to start about my work. As you heard earlier, I work at Bentley Systems. Our mission is to advance infrastructure with our engineering software solutions. We have a vast portfolio of products that cover everything in infrastructure, from roads and bridges to buildings, energy and water supply systems, and more. Like all of you, I am a structural engineer, and within Bentley's portfolio, that covers the STAAD brand, RAM brand, and ADITA brand. STAAD's flagship is STAAD Pro, which is a global leading general purpose structural analysis and design solution. RAM is focused nearly entirely on building structures, and ADITA is our advanced high-powered FEA product. My day-to-day responsibilities are focused on RAM Concept, for which I am product manager. RAM Concept is developed for the structural analysis and design of elevated concrete floor slabs and raft foundations. It is well known for its post-tensioning design capabilities, but it is very adept at conventional reinforced concrete design as well. And RAM Concept has a rigorous punch and shear design solution. It allows you to complete all punching checks in a single model, can consider irregular geometry, automates stud rail design, including the shear fix solution, and then offers an auditor for detailed calculation review. So that's enough with that. Let's talk about the new EC2 and punch and shear. And the remaining part of my presentation is going to focus more on the theoretical basis. I'm going to go to the theory behind the model. And then I'm going to also discuss some implications for finite element analysis, since that's important to me and also for RAM Concept. Harriet mentioned this, but while the first generation punch and shear equations were empirically derived, the second generation equations are based on a mechanical model, and that's called a critical shear crack theory. Critical shear crack theory models punch and shear failures by focusing on radial and tangential cracks around the column. That's shown there on the image at the left. And the theory assumes that the ultimate punch and shear capacity is governed by a single shear crack, and that's initially formed by flexure at the top surface there near the column. And it increases in width due to the rotation of the slab, and that's shown in the middle image. And you can see the rotation of the slab depicted there at the top. So in that image, you can see that there's a failure criterion curve. And that's determined using many interrelated concrete behaviors and properties. It's also calculated mathematically, so not empirically derived. And then it's also has been fit to test data, and that's shown there on the third, or the image on the left. The rotation equation in that punching shear model, critical shear crack theory, is shown at the top. You can see it's a function of the effective depth, the provided rebar, and also the moment demand and capacity at the slab strips in the column. That's MS and MR in that equation. So far, I've discussed the model in terms of slabs without reinforcement, but reinforcement can easily be considered in the failure criterion too, as shown in the middle image. In fact, the model is flexible, so it can be modified to fit other conditions, unique situations, since everything is mechanically derived and not based on that empirical data. So as we discussed, the slab rotation is an important part of this model. And I wanted to just take a short pause to highlight this article, which was recently published in Structural Magazine in the US. Also, I was just at the American Concrete Institute convention in the States, and this was one of the sessions. And as I watched it, it just struck me, there's bits and pieces here that fit into the critical shear crack theory. So the article in the study focused on existing structures with slender two-way slabs, so very low thickness. And those slabs all suffered from spiderweb cracking, which you see there in the photo on the left around the column, and also in many cases excessive deflection. And you can see from the image, if a building owner or an occupant saw that, that might be cause for alarm, right? But what the authors found is that these slabs still had plenty of reserve punch and shear capacity, and the cracking was largely a service issue, not a strength problem. And what they found is that slender slabs were more susceptible to the issue due to what they attributed to a tent pulling effect, just shown in those finite element models down at the bottom there. So you can see as the slab gets more and more slender, the deflected shape takes the form of a tent pole, so very aggressive slab rotation. Whereas if you have that smaller slab to depth thickness, you have a more gradual doming effect. The cracking is attributed to peak moments. If you focus on the top right image there, the peak moments at the column versus how the reinforcement is designed and detailed. And as you know, you design for an average moment across the strip, and you distribute your reinforcement accordingly across that strip. So the cracking here is initiating from those peak stresses at the column, and then there's a load distribution that's happening due to the way that the reinforcement is detailed across that strip in the average moment, and that's giving the reserve strength capacity. So the takeaway is to remember that punch and shear here, it's not just a strength effect. Don't forget about serviceability too, because those spider webs cracking are going to happen well before the failure occurs. So numerous studies have verified the failure criterion using advanced nonlinear FEA products. And in general, those products are required because they simulate the complex nonlinear behaviors like tension stiffening that are captured in that critical shear crack theory model. I did find one study that involved a linear FEA, and that was of interest to me because that is within the capabilities of RAM concept. So in that study, if you look at these images on the right there, they actually used an iterative process to determine the capacity. So I'm not going to go into all the details, but the process was iterative, and it followed that workflow. Essentially, they started with a small applied load, integrated stresses or the shear and moment across control perimeters to find the stresses. They then back calculated a punching shear load using that shear rotation equation and the critical shear crack theory model. And they repeated that iterative process until the applied load equaled the load from that calculation. So as designers, that's not practical. No one's going to use an iterative analysis right that to do a punching shear check at each column. And the code writers knew this. So they wanted an easy way for us to calculate punching shear that would fit our daily design work. So what they found is a closed form solution, and that was found by making some approximations to the model. And if you're interested in those, if you notice I have references here, but that reference will go through all the assumptions and has a good explanation of how that closed form solution would fit. And here is where we landed. Here it went through these equations. We talked about the beta factor already, that it's in place, maybe a little simpler. I'm going to talk about that here in a second. And I haven't talked about finite element analysis, or just maybe a small amount here, but this is really what I want to focus on here with the model, these two clauses. And Harriet talked about each of these, but the top one, design shear stress may also be calculated directly from a detailed analysis of the shear distribution along the control perimeter using a method accounting for equilibrium and compatibility conditions of the slab. And then as Harriet pointed out, the beta factor is missing there, and there is some guidance on how to average the shear in those zones. So one could read that and come to the conclusion that you could use a finite element package like RAM concept to do something similar. And then the second clause there is, again, Harriet explained this, but it's the distance from the center of that punching zone to the point of counterflexion. And that's another thing that can be measured with finite element software. You can look at your radial moment distribution around your columns and easily in each direction find where the point of counterflexure is. So if you went about that process of using your finite element package to determine those shear distributions, there's several things that you should keep in mind, and maybe some traps that you could follow. And one is you need to make sure that your model actually represents the structure, especially if you are calculating slab rotations and things like that. You want your model to capture the actual behavior. And one thing with finite element analysis products, it's easy to create a model. And if you look at the image of, say, a column, it might appear that that column is an extruded solid shape in the analysis. But for the most part, that's not the case unless you're using a high-end analysis product. And in concept, that's actually a linear 1D member that's attached to the slab at a single point. So if you think of that slab deforming, it's attached at a single point, not around the column. And if you think back to the tent poling examples, you can see if you had a lot of load that you could easily incorporate that behavior because you're attached to the slab at a single point. So most products on the market have ways to handle that. In concept, we have a rigid support zone feature that I'm showing in the lower right. And if you use that feature, you can enforce a stiffened zone there with custom stiffness factors that create meshed elements that are bounded by the column shape and just have an increased stiffness, so you can account for that region a little bit more appropriately. If you had a high-end product, maybe you have the option to actually use a solid element, and that would be the best for capturing that slab rotation behavior. Next thing to talk about is the Eurocode 2 has ways to deal with axial compression and tension in the punch and shear model. And with a finite element analysis, you can easily, under just gravity load, produce axial forces in your slab. And one of the most common cases for that to occur is at slab steps or depressions. And if you focus on the image on the top right, that is how concept would idealize that situation. So each of the shells are located at their centroids, and they're connected to adjacent or nearby shells with rigid links. And those rigid links, as that section bends, is going to induce compression and axial tension in the slabs. And I've shown that in a model there on the left. You can see that there's tension and compression in those elements. So when you have that case, you need to think about, because this is an important part of the load path, how is this accounted for in the punch and shear checks, or if you're just ignoring them completely, which may not be appropriate. And then finally, this article had a nice study, and I copied it. It's a parametric study, and I'm varying. So really what I'm looking at is how variations in mesh, how that stiffness factor and the stiffened zone feature, how would they affect calculated the A parameter, which again is the distance to that point of counterflexure, and then also the beta value. And you can see that these are elongated columns. And I believe Harriet did show well, if you look at a stress distribution along elongated column, you're going to expect peak stresses near the columns or corners of the columns. And that's another thing to keep in mind when you're dealing with finite element analysis packages, because if it's connected at a point, you're trying to determine or take out stress distributions, you're likely not incorporating that level of detail at the column, right? Because the corner of the column is not modeled. So these are results. I'm going to go through this fairly quickly, but you can follow the mesh size there. It's really broken into three zones here. So the first one does not, first 1 through 4 does not use the stiffened columns at all. We're just looking at mesh size. The next 4, I'm using a column stiffened zone, but I have a stiffness factor of 1. And the benefit there is, yes, I'm not stiffening that zone, but I'm improving the mesh, okay? So now that mesh is bounded by the column shape, so I have at least one element between the center of the column and where the control parameter is. And then the last one is identical to the last set of steps, but I'm increasing the stiffness factor by 10. If you look at the columns V, MX, and MY, those are the column reactions. And you can see that for the first 8, they're roughly the same, right? But once you put that stiffened zone in place, start seeing the moment increase. And that's significant because even if you weren't using an FEA package to take stress distributions out, that's also going to increase your eccentricities, and it's going to affect your beta values there. So I would urge you, if your package has a feature like that, to use it and analyze and design with these larger moments, because I feel that's more appropriate. So the last 2 is really what I was after here. So you can see the variation in that A value. I think for the first 8, they're roughly the same. Once I put that stiffened zone in there, that point of counterflexure started to move out. I don't think the provision that's in the new EC2 kicked in for any of these except for maybe the last one. The beta value is really maybe the important one here. And the way I went about this is I used a concept to take a stress distribution across those zones. I did follow the new EC2 and was respected the 2D restriction there. And you can see they're off the board, but as you decrease the mesh size, I was getting better results. As you increase the mesh size, I would say we're getting unconservative. And the reason that's occurring is if you think of the element attached to the column, you really want multiple shell elements between the column and where you're taking the stress distribution. But as that mesh size gets coarser and coarser, I'm distributing within a single element, and that's really skewing the results. So that is the takeaway. I would recommend not using a linear finite element analysis to do that and avoid the beta calculation. If you were doing that, I would recommend probably using solid column elements, better modeling that zone, and then also varying the mesh size between the column and where that control parameter is, and get as many elements across that zone as possible. So finally, I'll stop here. While researching this, I found some fantastic articles. I've listed these as references here. If you do have the time and are interested in the subject, I think all of these are good to review. With that, I'll turn it back over to Jennifer. Thank you.
Okay, so thanks very much to all of our speakers tonight. So we have a summary here of what we've covered in the talk today. So we've talked about the new changes coming to the Eurocode and some practical tips on how to implement those. And particularly, I think the focus on the boundary conditions and the importance of getting your modelling correct and mesh size correct is really important. I also meant to say there are people joining us online tonight, and we are monitoring the Zoom. So if you'd like to submit questions online, we can also answer them here too. But before that, can I open to the floor if anyone would like to ask any questions, and maybe the panel can come up and sit at the front. I guess also maybe if you'd like to comment, I think we didn't mention the TR43 publication that's just come out from the Concrete Society and how that interacts with EC2. Do you have any comments on that? Anyone from the panel? No? So I'll just make the point that there is another publication, TR43 Guide to Post-Tension Slabs, and it's also just been published by the Concrete Society, and it's in line with the Eurocode too. Does anyone else have any questions? Don't be shy. Oh yes, yep. I'll just repeat that for the people on Zoom. So it's a question about getting more out of studs versus links, and what's the science behind that?
It's been proven through testing quite thoroughly. The real science behind it, I'm not sure on any more than that, but you get the capture from the sort of
Well, I think in the second generation of the Eurocode also will verify that.
Around 20 to 30% higher capacity when you are designing with rail compared to link. And also in terms of installation, it's much easier to install rails. And it's much easier to fix them compared to links, because with links, they are always, or most of the time, are installed incorrectly or not tied properly at the bottom.
The RAM concept slide where you have the different results. I haven't used RAM. Now, how does it deal with like crack section properties, like adjust the slab and the column to get the elements getting into it?
Right.
Sorry, I'll just repeat that for online again. It's for the RAM concept, how it deals with crack section stiffnesses.
So one of those images I showed, taxes, those were in terms of that rigid support zone, but the slab area has that same option. So if you want to do crack property, it's just a matter of entering a value less than 1. I will also say that if you're looking for deflections, if that was a concern, Concept and other products have more detailed ways to go about that and automate that and calculate a stiffness factor and incorporate it into a nonlinear analysis. So those tools are available too. In that case, you wouldn't need to enter a stiffness factor. You let the program calculate it through its calculation.
Can I ask for a quick show of hands of who actually is using or has used RAM concepts in the room? Just a couple of people. And who's used the Leviat tools before? Okay, so I've got a few more. So I'd also just like to say that we'll be hanging around afterwards if you'd like to talk to us. But Carl is visiting us from the States this week and we'll be here until Friday. So I'd like to extend a welcome to anyone that would like to come in and see our fancy new offices. We've got a really amazing view, if nothing else, of London from the 43rd floor. And we're available this week. If you'd like to come in, just let us know. Any other questions? Yep. Uh-huh.
How does the stiffness of the support, in example, considering that as a spring rather than rigid, affect the outputs as compared with the EC2 generation 2 calculations?
So hopefully people can see that online, the question is kind of.
So a spring, I think you would run into the same issues. Likely that spring is, I'm guessing, a point spring, although you could do an area spring, I guess. But I think modeling it as an area spring would be more difficult to model the bending stiffness. But it's really would fall exactly what I explained for the column.
Any last questions? Oh, how was that? No. Okay. I mean, I know it's quite hard to ask questions in a room like this. So if you'd like to come up and speak to us afterwards, we'll be heading upstairs. And please come and help yourself to the food because it'll go to waste otherwise. And we've also got drinks up there. So, so thank you all for coming again. And hopefully we'll see you upstairs. And thanks again to those online.